All right, how's it going, folks? Today we're going to chat about glacial erosion, right? We talked about water being the number one agent of erosion. Well, that's true when you look at a whole world as an average, but the further north you go, of course, glaciers living in the north become more and more of a force to be reckoned with, right? More of a significant agent of erosion. That's what we're chatting with today. But before we, of course, get into that, we need to realize that if you're a Long Islander, then you're kind of a Canadian citizen because glaciers pushed all their sediments down from the north through Canada, that Canadian sediment, and then stopped advancing and kind of dumped it right here, and that's what Long Island is. So, got to give a little respect to where it's due. Come on, you know the words. Or maybe you don't. All right, you get the gist. But yeah, so the glaciers came down from the north, pushed that, broke up Canadian rock and then pushed it south and then stopped advancing right around where we are. This episode happened at least twice, right? They said there's at least two glacial deposits that make up Long Island, the North Fork and the South Fork. But yeah, all this sediment used to be all the way up north. Pretty crazy stuff. All right. So read through your definition there. How do we define glaciers, right? They're kind of like rivers of ice. Hit pause and read that through. Okay, and there's your official definition. Large, massive ice slowly moving across the landscape can carry any size sediment, right? With the river, we were calculating velocity to figure out how big a sediment it could erode. Well, glaciers can pretty much push it all, right? Any size boulder, no problem, and all it gets pushed. And then, of course, when it stops advancing and melts, then that boulder just stays there. They call those glacial erratics, and we'll talk about that. So there's valley glaciers, right? Ones that kind of carve between mountains, and then there's continental ice sheets that just literally barrel across a whole continent. And take a look at some of these numbers, folks. These are, of course, if you remember, contour lines, right? They show thickness in this case, elevation. Look at how thick some of these ice masses are, right? You're talking about 3,000 feet. That's way, way thicker than the Empire State Building is tall, okay? It just blows you away. Look at this one here, 35, even 4,000 feet thick. The thickness of this ice is mind-boggling. It's way taller than any skyscraper in the world. Okay, these ice sheets are way thicker than that, and of course, as they melt, that water goes into the ocean and sea level rises. Right, that's where you get that sea level rise from. So check this out: how do glaciers move? Check out the animation. You get snow up in the mountains, and under the pull of gravity, well, down they come. And notice the shape they're carving is a U shape, not a V. Right, the rivers were the V. And it'll keep pushing down, keep advancing during a period of global cooling. And then during a period of warming, right, the temperature is now warmer, so the melting, it becomes faster than the snow accumulation, right? There's the sun representing a global warming scenario, and it will start to retreat back up the mountain. Now, it's not that it's going in reverse, it's just that what was on the front has melted, and of course the water now drains out. You get this temporary river as it comes out of there. And a lot of people around the world depend on glacial melt for their fresh water supplies. So the whole disappearing glacier scenario gets people concerned because that's where they're getting their fresh drinking water from. Okay? Well, how do glaciers move? Right? They're either advancing or retreating. They're never staying still because climate is always warming or cooling. And when they advance, it's during more of an ice age period. They retreat during more of a warming period. Okay. And here you can see scientists taking some measurements on how quickly it's retreating, because that's directly related to, of course, a warming scenario. And they want to make sure that, if it's retreating crazy fast, well, that sets off the alarm bells for, whoa, what's going on? And of course, our pollution, as we know, certainly seems to speed up global warming, and that's a concern for many people. All right. The sediments that are left behind, not like a river, they're not sorted, they're not polished. No, they are unsorted, unlayered. They tend to be scratched, but certainly will not be round and smooth like those river rocks. Okay. Here you can see two different pictures. This is from about 80 years ago, and this is today. So obviously we've been in a period of warming, so you can see this ice sheet getting smaller, and that's up in Alaska. Okay. Just like a river, right? We talked about these vectors where they're longer, it's going faster. And you can see, just like a river, it goes faster in the center, right? It's not scratching the sides. However, over here, the top goes the fastest. In a river, it was a little below the top because of air resistance, but a glacier doesn't have air resistance, right? It's not moving with the speeds that a river does to get that resistance. So fastest in the center and slowest at the sides where it's grinding the valley walls. All right, if you increase the slope, of course, it will advance faster. Okay, a couple more great shots. Aerial views of a valley glacier advancing there. Okay, little comic relief for you there, right? All this fear of global warming for you. So this is the far side. And how fast did these glacial monsters move? Well, it says, say thag, wall of ice closer today, no? And the joke is that during the Ice Age, it's inferred glaciers could advance as much as several meters per day. And if that's the case, and if this is the direction of advance, then what's going to happen to these guys tomorrow? Right? That glacier is going to be at their front door, and they're going to be stuck in the cave. So kind of a comical make fun of the simple caveman type of thing. All right, how does the glacier erode sediments? There you have it. It'll literally drag them across this rock and grind them and pulverize them into smaller pieces, and it'll leave these long linear scratches, which you could still see in Central Park today as these striations in the rock. And they usually come from the north-south direction, right? That's the direction glaciers are going to come from. And they call them glacial striations, and there they are, those gouges that a glacier carved into the bedrock beneath it. Okay? Anybody recognize that shape there? I sure hope so at this point, right? That's your classic U shape. Glacier, right? Just like it was river with the V, now it's glacier with the U. I know there's no U in glacier, but you got to kind of force it there to make it happen. They make U-shaped valleys as the ice expands. Drumlins are another cool glacial feature. As the glacier advances, it'll carve out, again, this north-south strange shape in the ground. This one you can see looks like it was cut by an earthquake afterwards. So kind of a lot going on there. These are all over upstate New York. All over upstate New York. All right, you got an aerial view map of a topography map. You can see them all over the place. Your flow direction, they're always going to be a little bigger in the front. They taper off toward where they're moving. All right, so this must be coming from the north, and that's toward the south. All right, there you can see it again. Just kind of a side view. This would be where it's coming from. That's where it's going. So this must be towards the north, and this way towards the south. Okay? All right. So you have a couple of summary questions there. Put some love into those, and we'll chat about them in the meet. See you there.